starting us out with the scenario. A friend wants to play a simple coin flipping game. If the coin lands heads up, you win. If it lands tails up, your friend wins. So let's suppose we play 5 times and your friend wins every single time. Do you think your friend is cheating? No? You trust your friends. You guys are trusting people. So what's the probability of this happening? Each time it's a 1 in 2 chance. So to get a tails the first time is 1 in 2, and means multiply. The second time would be 1 in 2, and the third time, and the fourth time, and the 5th time. What is that probability? Multiply it for me. 1 over 32, or what is that as a decimal? What's 1 divided by 32? Okay, so is it impossible? No. Is it unlikely?
Yes.
Yes. So my conclusion, either our friend is lucky or cheating. Could be either one. It's not impossible for this to happen, but we really wouldn't expect it to. It does fall into the unusual category. So hypothesis testing is basically taking this type of scenario and figuring out, like, is it more likely that this was just luck, or is it more likely that your friend was cheating in this scenario? When we make a hypothesis, you've seen a hypothesis in your science classes, it's just a statement. In your science classes, you're thinking more of like an educated guess about what's going to happen. Here we're making some kind of statement, usually about the mean or the proportion, like we're going to assume the mean is 5, or we're going to assume the probability would be 1/2, something like that. So in this scenario, in 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes the percentage is different today, so that's their hypothesis. It was 62%, the hypothesis is it's not 62 anymore. It has changed in some way. According to a study, the mean length of a phone call was 3.25 minutes. The researcher believes that the call has increased. So it used to be 3.25, the hypothesis is it's more than 3.25 now. This stuff is only necessary when we don't have population data. You know, if I actually have every phone call made in the last year for the entire United States, could I figure out if the mean length is still 3.25? Absolutely. So this has to do with inferential statistics when we're trying to make a guess about the population. If we actually had the population, we wouldn't need it. So when we do hypothesis testing, we are going to go through a few steps. So we're going to make a statement regarding the nature of the population. We're basically going to make our hypothesis. We're going to look at the evidence. So we're looking at a sample. And then we will decide, is this correct or not? With our format, we are going to focus on a null and alternative hypothesis. So the null hypothesis, we put an H sub 0. This is basically our starting hypothesis. This is assumed true unless the data proves otherwise. So a null hypothesis, we are not actually going to try to decide if the null hypothesis is true or not. We are going to assume that's true, and we're trying to prove that it's not. So then the alternative hypothesis is what we are trying to gather evidence to look at. We're going to set them up one of 3 ways. So in every problem, we'll make our null, and then we'll make our alternative hypothesis. So the null hypothesis will always be an equal to. The mean equals 3.25. The proportion is 1/2, so that will be an equal to. Then the alternative, we could have the mean is less than 3.25, the mean is greater than 3.25, or the mean is not equal to 3.25. So we'll have 3 different options there. So we have, those are classified different ways: two-tailed, left-tailed, and right-tailed. In every scenario, the null hypothesis is the same. If it is two-tailed, then the alternative hypothesis has a not equal to. If it's left-tailed, we have a less than. And if it's right-tailed, we have a greater than. So the first example we're going to do, we're just going to read a scenario. We are going to write the null and alternative hypotheses for these. And then we'll say if it's left-tailed, right-tailed, or two-tailed. In 2008, 62% of Americans regularly volunteered their time for charity work. A researcher believes this percentage is different today. So my null hypothesis, you have to put the sub-zero so we know it's the null. The null hypothesis is always equal to. If I'm talking about a percent, what variable do we usually use when we're talking about the percents? P, it's a proportion. So it would be that the P equals 0.62. Then the alternative, we call that H sub 1. We just said different. So different would be not equal. Yes. So then I want to know what kind is this? This is a two-tailed. I didn't ask this, but my parameter, the parameter, if I ask for it, is just the variable. So in this case, it was P. We were looking at proportion. It could be like an X bar or a mean or a sigma, any of those things. So the parameter is just our variable. All right, B. According to a study in March 2006, the mean length of a phone call was 3.25 minutes. The researcher believes it has increased since then. So my null hypothesis, mean, X bar or mu. Let's just go with mu. It will assume population was 3.25. Your null hypothesis is always an equal to. So the alternative would be what? Greater than, because we think it's increased. So that's greater than. All right, is that left, right, or two-tailed? Right. If you think about it, you know, if you're here, if you're greater than, that's to the right, so this is right-tailed. What's my parameter here? Okay, C. Using an old manufacturing process, the standard deviation of the amount of wine put in a bottle was 0.23 ounces. With new equipment, the quality control manager believes the standard deviation has decreased. So null hypothesis. Standard deviation is sigma equals 0.23. Alternative. Sigma is less than 0.23. Left, right, or two-tailed?
Left.
What's my parameter here? Is that one okay? The second thing that I want to talk about today is error, we have two different types of error, which are essentially mistakes that we might make. So there's type 1 and type 2. Type 1 would be when we reject the null hypothesis, but it's actually true. So it would be like me doing this experiment and saying, yep, the standard deviation has decreased, but it really didn't. Okay, so type 1 is when we reject, but we should not. Type 2 is the opposite, when we don't reject, but we should have. So it would be like me concluding in this scenario, nope, there's not enough evidence that it has decreased, but it really did. Okay, so my mistakes, either I don't reject it and I should have, or I reject and I should not have. These have variables associated with them. So alpha is the probability of making a type 1 error. Beta is the probability of making a type 2 error. That will have more bearing later on. Right now we're just trying to talk about a few of the things that are going to pop up in this chapter. So what I want to do is take a couple examples and write out what it would mean to make each type of error. So in this one, I want to give the example for type 1 error and type 2 error. So in 2008, 62% of adults regularly volunteered their time for charity work. Okay, that's the example A that we wrote back here. Type 1 error is we reject the null hypothesis, but it's actually true. So a type 1 error would be if the researcher concludes, if we reject it, that means we believe it's different. But it's not. So in type 1 error, you are accepting the alternative hypothesis and you should not have. Type 2 error is the opposite. So
researcher concludes percentages true in saying it's different.
So if we conclude it is still 62%, but it has changed. Do you guys see the difference in these? So basically in type 1 error, you think the H sub 1, the alternative, is true. In type 2 error, you're going with the null hypothesis. But in both scenarios, you made the wrong conclusion. So, our cell phone example. Hello. No. Sorry. Okay, bye. All right, so type 1. So in type 1 error, you are going with the H sub 1. So it would be like me saying, okay, this is true. So the researcher concludes the mean is bigger than the 3.25, but it is not. I remember it by thinking the H sub 1 and the type 1 go together. Okay, so what would type 2 mean? In type 2, you are going with the null. So the researcher concludes the mean is still 3.25, but it's not, it has changed. When we are looking at these, we never accept the null hypothesis. Basically, we have two different things. We are trying to prove the alternative. So if I don't have enough evidence to prove the alternative one is true, that doesn't mean the first one was. So as we go through this, and we will practice this a lot, we'll do a hypothesis test and we'll always state our conclusion. We are not proving the null hypothesis is true. We have just failed to prove it's wrong. Okay, so we're not proving it's true, we're just trying to prove it wrong. So we won't say we accept the null hypothesis, we'll just say we can't reject it. So the last example for today, I just want to practice the wording of how we would state our conclusions. So this is the phone call example for the 4th time here. So we do this hypothesis test, and let's suppose the evidence indicates the null hypothesis should be rejected. How would we write that conclusion? So we would say there is sufficient evidence to conclude all right, in this one we were looking at what was the null hypothesis in this example? And the alternative was that the mean has increased. So if we reject the null hypothesis, that means we are going to accept this. So there is enough evidence to conclude the mean phone call length has increased. Okay, if it was a less than, we prove that it decreased. If it was not equal to, we just proved that it had changed one way or the other. All right. Then the other option is we do the experiment and we don't get evidence that we should reject it. So does that mean we conclude the mean phone call length is 3.25 minutes? No, that's not what we are trying to prove. We are trying to prove this false, and we couldn't. So we just say there is not enough evidence to conclude the mean call length has increased. Okay, we failed to prove the alternative, so we couldn't conclude it had increased. Any questions there? So this is a pretty short lesson. I have a homework packet for you. Now this is actually all of chapter 10, so don't freak out when you see 3 pieces of paper, but only the first 5 questions are from this section. So I think you should be able to get those 5 questions done before the